All right. Now, ionic bonds are governed by something called the lattice energy. And what a lattice energy is, it's the amount of energy, as you can read here, the amount of energy required to convert 1 mole of ionic compounds to constituent ions in the gas phase. It's a lot to take in, right? But at this point, we're looking at the energy of formation is not the lattice energy, okay? But it's a component of the lattice energy. Because these ionic structures, when they form their crystals, they're very well ordered and well packaged. So the heat of formation that's associated with these things is not the lattice energy, because the two aren't equal, okay? So lattice energy, what it is it's sort of a compilation of various different energies that we can calculate inside of something. And to get there, what we use is something called the Born-Haber cycle. Right? And it consists of 5 parts to give the actual lattice energy. The first part is going to be the delta heat of formation. Right? Then this is the amount of energy that's either required or released when something is formed. Okay? So it's the base energy of something. So this is the heat of formation is the first part. Okay? The second part is the heat of sublimation. And this is generally the amount of energy required to go from a solid to a gas. And this generally has to deal with the metals that we're dealing with. So this is delta H sub. And this is the heat of sublimation. Okay, it's a phase change. Okay, so this is going from a solid to a gas. Okay, so for example, going from solid sodium to gaseous sodium. Okay, all right. One of the next energies that we're going to deal with is the amount of energy required to ionize something. So we've run into this before. This is the ionization energy. So delta H ion is the ionization energy of a metal. Hopefully I spell it right. Ionization of the metal. Okay, and this is generally where sodium gas goes to sodium gas with an ion associated with it. All right. If you deal with something that is like calcium, alkali earth metal, you have to account both the first and second ionization energies and add them together. Okay. The second ionization energy does not take into account the first ionization energy. So if you're given calcium, you've got to add those two together to get that lattice energy. Okay. The fourth component of this is the delta H of electron affinity. Okay, remember, when I talked about electron affinity before, I talked about all those positive values. In general, those positive values are going to be negative here, the negative delta H. So this is electron affinity. Of the nonmetal. Okay, and that's why something like chlorine gas goes to Cl gas with a minus. All right. The lattice energy may or may not be needed. It depends on the value that you've got, all right? And it's how much energy that's going to be required to convert chlorine gas into atomic chlorine. So I'll put this delta H of the bond cleavage. And the delta H of the bond cleavage is when you are separating Cl2 into 2Cl. Both of these are in the gaseous phase. All right? And this covers a lot of things. Now, there's one thing that I have not covered, and that's bromine. If I get to bromine, bromine is a little bit more tricky because it's a liquid. So there's a sixth step. You have to go from liquid bromine into gaseous bromine. And iodine is the same. You've got to sublime iodine from its solid state to its gaseous state. Okay? So these are all the parts. If you add up the sum of all of these parts, what you're going to get is the lattice energy. So one way of looking at this is to say that the delta heat of formation plus the delta heat of sublimation plus the delta H of ionization plus delta H electron affinity plus the delta H of bond cleavage. All of these are going to give us, let's see, do I have it all on the screen? Yeah, there we go. Okay, good. All of these are going to give us the delta H L, which is the lattice energy. Okay? Now, you look at this and you're like, oh, there's so much math. Oh yeah, there is math that's associated with this because this is a sum of several different substituent parts. Okay? The Born-Haber cycle is one of these cycles that we can look at and we can try to predict what these are based on values that we've measured in other parts of science. Okay? If I look at this as far as a table goes, all right, in general what I start with is a, whatever the compound is, and it starts with the delta H of formation, the delta HF, and the next step that we go to is the delta heat of sublimation. That's delta H sub, okay? And at this point, what I'm going to do is I'm going to write down what these things are. So this is NaCl solid, okay? When I go to delta H sub, I am changing the solid of sodium to the solid of gas, okay? And on this level, what I'm then going to do is go up to the next level, and this is delta H of ionization. And what I've done here is I've transmuted sodium gas to sodium gas ion. Okay, so I should take in that. So that's this step right here, the ionization energy. And then I go to the next step. And the next step is the cleavage of Cl2. Right, so this is delta H bond cleavage. So the chlorine gets separated. I'll write it this way so you can see it a little better. So there's chlorine gas. And this gets separated into 2Cl gas. Right, and for the most part, electron affinity, we're going to gain some energy back on this. So it's the only part of this that goes back down. And what this is the delta H of electron affinity. And what that is when the chlorine that's in the gaseous state goes to Cl minus. Okay? Now the differences that I have here, this big difference that I've got here at the end is the lattice energy. So everything that's in here is my lattice energy. All of those added together is going to give me a lattice energy. And for the most part, that lattice energy is how much energy is really bound inside these ionic crystals. All right? Bear in mind that there are some things that you're going to have to keep in mind. Notice that at this point I've used 2 chlorines to get the Cl2. Let me tilt this a little bit. All right? I've used 2 chlorines to get the Cl2. In order to get that value, I've got to take half of that value. So say the value is 250. In this case, I've got to use half of that, or 125. Okay? So for sodium chloride, I'd have to use 1/2 of this value. Okay? Same with any metals. If I suppose I had sodium oxide, by going from 2 sodiums to the oxide, I'd have to multiply this by 2. Okay, for each one of these, because both of those sodiums have energy consequences associated with it. Okay, so that's essentially what the lattice energy is. So if I give you a problem like this, you should be able to at least solve this problem.